In the previous video, we talked about the gradient for scalar fields and the directional derivative. Now we will extend it to vector fields and talk about the relevant differentiation operations we have here. Start by defining the vector field V. Assume that we want to calculate the partial derivative with respect to x. This is achieved by taking the partial derivative for each component separately. The same would apply if you take the partial derivative with respect to y or z as well. All of these three equations describe vectors. Now, let us recall that the gradient operator is the partial derivative with respect to x in the x direction, with respect to y in the y direction, and z in the z direction. Let us apply this operator to the vector v. If you take a look at the x-hat term from the gradient, this term in itself is a full vector, as v is a vector. The y-hat and z-hat terms are also full vectors themselves. Before we continue, let's recall that we can write the vector as either a row vector or a column vector. The gradient of v contains 3 vectors and is therefore a tensor of rank 2. There will also be 2 different ways of writing this tensor. The first is to insert our vectors as column vectors. This is called the numerator layout. It's also the common form to write the Jacobian matrix. The other option is to insert the vectors as row vectors. This is called the denominator layout. I will use the denominator layout in this course as I think it's more logical with respect to how we write our equations in fluid mechanics. Be aware though that both are being used and the matrix operations will be different depending on which layout we use. In the denominator layout, we can write the vector gradient as the following matrix multiplication. Insert the gradient operator as a column vector and the vector v as the row vector. This is the same matrix operation that creates the dyadic product. As a repetition of the matrix operations, let us look at the convective acceleration term from the previous video. In our denominator layout, this will translate to the row vector v multiplied by the vector gradient. This is solved by matrix multiplication. Start with the vector times the first column. Continue with the second column. And the third column. To save space on screen, I'll change it to the column format, but add the transpose sign to keep the matrix multiplication valid. We can replace the vector gradient by the matrix multiplication that generates it. As matrix multiplications are associative, we can do the left part first, as we did in the previous video. This will give the same expression as before. Note, this is only for Cartesian coordinates. Please watch the cylindrical coordinates video for details on how to handle the vector gradient in other coordinate systems. Let's do some more repetition of the vector multiplication videos. Start with the dyadic product, which corresponds to our vector gradient. We also had the dot product, which is the sum of the diagonal elements of the dyadic product. The dot product is multiplication with the parallel parts of the vectors. The corresponding operation for differentiation is the divergence written as nabla.v. It will be the sum of the diagonal elements of the vector gradient. We will come back to the interpretation of this operation later. The other multiplication operator we have is the cross product. It will be given by the off-diagonal elements of the dyadic product. The difference between these give the x value. These two give the value. And these the z value. The geometric interpretation of the cross product is that its length is given by the area of the parallelogram with the two vectors as sides, or a multiplication with the perpendicular parts of the vectors. Its direction is the normal vector of the parallelogram. The corresponding operation for differentiation is called the curl, or the rotation, written as nabla cross v. It will consist of the off-diagonal elements the same way as for the cross product. To start, let us show a very simplified vector fields to illustrate these operations. Start by a velocity in the x direction that linearly varies in the x direction. We see that the dvx dx term is the only term in the divergence that will give a value, which is k1. Every single term in the curl will be 0 in this case. Next example, flow still in x direction, but let it vary linearly in the y direction. Now it's only one term in the curl that gives the value minus k2. All other terms are 0. Hence, when the flow varied in the direction of the motion, we got the divergence, similar to the dot product, which is multiplication with the parallel parts. When the flow varied perpendicular to the flow, we got a curl, similar to the cross product, which is multiplication by the perpendicular parts. It's a little bit more advanced though, as we will see in the following examples. To get a better understanding of what the divergence actually is, let's look at a two-dimensional case. For simplicity, we are going to use an axisymmetric case and use polar coordinates to describe the flow. Now we are going to assume that for a circle with radius below 1, it will have constant divergence d. Outside the circle, we will assume that the divergence is 0. Inside the circle, we get the following expression for the divergence. Note, in polar coordinates, the expression for the divergence will be different. I will cover the derivation in the cylindrical coordinates video. For now, just remember that you cannot use the expression for Cartesian coordinates in other coordinate systems. To get a unique solution, we need to add the additional condition that the flow is irrotational and that the flow velocity far away is 0. Due to our axisymmetry, this will give that v phi is 0, as we assume that there is no rotation. To solve this, start by multiplying with r and take the integral on both sides. The integral over a derivative is the function itself. And this is the integral over a polynomial. Remember to add the integration constant c. We can divide by r. What remains is to determine the integration constant. For r smaller than 1, use that 1 over r goes to infinity at r equals 0. As this is not physical, c has to be 0. For r larger than 1, we know that d is 0 from the condition we set at the beginning. However, as r equals 0 is outside this region, we can have a value of the integration constant c. The final condition we need is that both regions should have the same velocity at r equals 1. Hence, when we insert r equals 1, we get that c is d over 2. And we have solved the velocity field for the condition of constant divergence inside the circle and 0 outside. Let's have a look at this vector field if d is positive. We get that the circle is what we call a source, and the vector field has its direction outwards. If we change to negative d, the circle becomes a sink, and the flow goes to the center. Note the results we had in the pipe example that divergence was derivative in the direction of the flow. Does not fully apply here, as the velocity v changes outside the circle where the divergence is 0. To get a better visual interpretation of the divergence, add particles that travel with the flow velocity. Note what happens to the density of the particles. Outside the circle, the density of particles is the same. Inside the circle, we see that the density of particles increases significantly. Hence, a visual interpretation of the divergence is that if the vector field causes the particle to have the same density, the divergence is 0. Negative divergence will cause an increase in the density and positive a decrease. An alternative visualization is to consider a region that contains exactly the same particles over time. If this region has constant volume while it deforms, there is no divergence. If the region gets smaller, the divergence is negative, and if it gets larger, the divergence is positive. Note, this particular velocity field is not realistic in physics, but you will find similar vector fields in, for example, electromagnetism. Let's continue with another example with a pipe. Place the divergence in the red region in pipe. Outside this region, divergence is 0. Assume that the inlet velocity is v0. Now we can solve the flow field, but first noting that it's only the dvx dx term that will give a contribution, as the flow is in the x direction only. Integrate both sides. The integral of the derivative is the function itself. The integral of a constant is dx plus the integration constant c. If we define x equals 0 at the start of the divergence region, we can directly identify that v0 equals c when x is 0. And we get an equation for the flow in the divergence region. Outside, the flow velocity is constant on both sides. Let's illustrate this flow with the moving particles as well. They start with a constant density. When they reach the divergence, they accelerate and the density decreases. After, they continue with the constant density. Hence, we see that the positive divergence causes a decrease in particle density. Let us do one more example, but change the value of the divergence to minus d over 2. This would give a flow that slows down when we have the divergence. Now, we can add the particles as well. Again, they start at constant density. When they reach the divergence, they slow down and the density increases. After, they continue with the constant density. And we can conclude that the negative divergence increases the particle density. Next, call the length of the divergence region delta x and assume that the total divergence is constant. This means that if we reduce the size of delta x to half, we double the value of the constant d to get the same total. Now, if we change the length to delta x, we get that the final velocity at end is constant. The only thing that changes is how fast we are changing the flow velocity. The limit is when we let delta x go to 0 with d going to infinity, which causes a jump in the flow velocity. This may not be our typical application for fluid mechanics, but is commonly seen in electromagnetism when we have a charge distribution on the surface of an object. Now I will draw pipes with contractions, and first add a flow velocity that is constant between the wide and narrow parts. Then draw a pipe where the flow velocity in the narrow region is double that of the wide region. Which one of these flows is divergence free? If you think about what we have said about the particle density, I encourage you to try for yourself and figure out which one it is. So pause the video if you need more time. To get the solution, let's watch the two animations with particles included. From the animation, we can clearly see that the density in the upper pipe increases in the contraction. The density in the lower pipe stays the same. Hence, this is the pipe that has divergence-free flow. To say some more words about divergence-free flows, define a volume as the orange dashed line. In fluid mechanics, we call this a control volume with the abbreviation CV. The surface is called a controlled surface with the abbreviation CS. I will jump ahead a bit in the course material and mention Gauss' theorem here, which I will cover more in details in later videos. Here, we'll do a simplified version as the divergence is 0, hence the integral over 0 is 0. What we are left with is that the surface integral of the flow is 0, which has the practical implication that the flow in to this volume has to be the same as the flow out of this volume. To demonstrate it with another example, assume that you have two merging pipes and define the control volume around the merge. If the flow is divergence free, the flow in should be the flow out. Hence, if you have 1 liter in for each of the two pipes, the flow out should be 2 liters per second. Assume that all diameters are the same, this would give that the flow velocity out is twice the flow velocity in. In fluid mechanics, we would call divergence-free flow incompressible flow, as the density stays the same. Let's do one final example and look at an expanding pipe. Now we will study the field lines, also called streamlines. For a divergence-free field, these field lines cannot have a start point nor an end point. They will either continue with infinite length or they will form closed loops, as we see here. I will explain in the fluid mechanics course why we get the closed loops after expansion. Finally, I will just list the product rules for the divergence. If you want to prove them, it can simply be done by writing the expressions component by component and confirm that both sides of the equations are equal. Our first product rule is the divergence of a scalar f multiplied by the vector a. This will be the gradient of f dot a plus the divergence of a multiplied by f. Note that the gradient of f dot a is the directional derivative of f in the direction of a, multiplied by the length of a. The next case is the divergence of a cross product a cross b. It will be the curl of a dot b minus the curl of b dot a. Remember the minus sign here, which relates to that the cross product is anti-commutative. The final version is the divergence of a dyadic product of a and b, which is the divergence of a in the direction of b plus the directional derivative of b in the direction of a, multiplied by the length of a. Note that this one is not symmetric. This will be the end of the divergence video. Next up will be the curl. Thank you.